Greetings, everyone. Welcome to the ION webinar, Navigation Using Carrier Doppler Shift from a Low Earth Orbiting Constellation, Transit on Steroids, published in the fall 2021 issue of Navigation. Today's webinar is being presented by the paper's author, Professor Mark Psyche. Professor Psyche is the Kevin Crofton Faculty Chair in the Department of Aerospace and Ocean Engineering at Virginia Tech. He received a BA in physics and MA and PhD degrees in mechanical and aerospace engineering from Princeton University. He's a fellow of the ION and a fellow of the AIAA. His research interests are in the areas of GNSS technology, applications, and integrity, remote sensing, spacecraft attitude and orbit determination, and general estimation, filtering, and detection. We greatly appreciate the time and work that Professor Psyche put into the webinar. Following the presentation, we'll take your questions. To ask a question, you can click on the Q&A box in your viewer, and we will address those directly with Professor Psyche. So now, thank you for being here, and we'll turn the time over to Mark.
Well, thanks a lot for coming to listen to my talk here. Yeah, this is a subject I've enjoyed working on a lot, and I have hopes for it maybe blooming into a real system, but we'll see. So yeah, and I call it transit on steroids because it's really harkening back to the original transit system back in the late 50s, early 60s that was using Doppler shift to navigate basically ships at sea. And the steroids are the fact that instead of seeing one satellite every hour and a half or 2 hours, you might see 80 satellites all at once. And those are the steroids that it needs to do something better than the 200-meter kind of accuracy that the transit system was getting with a once every 90 minutes update. So the idea is that the overriding goal is to provide some sort of alternative or backup to dedicated GNSS from a medium Earth orbit, and to make it global, and to achieve really a 4D position navigation time, so three position components, time component, and just do passive reception of downlink signals from these large LEO constellations. And so I took the approach of using only carrier Doppler shift rather than pseudorange, in the hope that you can obviate the need to have atomic clocks on the satellites. Now, you might say, wait a minute, you don't need atomic clocks on the satellites because if the satellites have GPS on themselves, then they can GPS discipline their oscillators to be almost like atomic clocks, and you could do pseudorange from these constellations. But really, if you want to be a complete alternative or backup in case MEO GNSS really fails, you don't want to have your system relying on the satellites getting GNSS signals either. And so you either have to then have atomic clocks or skip pseudorange. So if you just do Doppler, all you need is a fairly stable frequency. The next thing I want to do is do point solutions. So I just want to, just like the beauty of existing pseudorange-based GNSS is that you have these 4 or more pseudorange equations, and you just solve essentially what is a batch filtering problem. It's a static problem. Just where am I now? What is my clock offset now? Without any reference to where you were a second ago or what your clock offset was a second ago. Now, if you want to add some dynamic filtering, you can, but you don't have to. And it's beautiful. You can teach seniors and juniors in college to get that to work. And so the idea is, can we do something like that with just Doppler shift? In order to do that, though, because Doppler shift is affected not just by position and clock offset, but also by velocity and clock offset rate, you got to solve for all 8 of those things, which means you need 8 or more satellites. It turns out you also need constellations that provide sufficient geometric diversity in the sense that we're used to in pseudorange-based GNSS. But as we're going to see later in the lecture, it's also important for their line of sight rate vectors. So these unit vectors that are pointing from the satellites to the user equipment, not only do they have to have geometric diversity, but their rates of change, which are also vectors, have to have sufficient magnitudes and their own geometric diversity in order for this to work reasonably well. So what I'm going to talk about for the rest of this session is, first of all, I'm going to briefly cover some related research. then spend quite a bit of time on carrier Doppler shift measurement models. These are really important, and it seems the literature is not very good about what constitutes a good carrier Doppler shift measurement model. I've only seen like one other paper that gets close. Then I'm going to survey large Leo constellations to see which ones might be suitable for a Doppler-only PNT. I'm going to develop a Gauss-Newton batch least squares filter. That's essentially the generalization or the replacement for the pseudo-range equation solution. It's going to be the Doppler shift equation solution with 8 or more Doppler shifts. Going to look at some simulated data and simulate the performance of that filter, including simulating ephemeris errors and clock frequency errors for the constellation. Then I'm going to develop a generalized GDOP analysis for Doppler-only PNT. This piece of work was a few years coming. I started into an effort on it, and it didn't really pan out. And then finally, in time for the 2020 conference, I managed to get this to work out. And it really gives insights into what's important about this system, what has to happen to get a good position estimate, good velocity estimate, and what the constellation has to be like. Then I'll use that analysis to map out GDOP for some constellations and show some good and bad constellations. And then I'll have a little section where I talk about some additional considerations that have to be addressed in order for all this to be anything more than just pie in the sky. And then I'll summarize and give some conclusions. So a lot of people have gotten interested in LEO constellations for navigation. Greg Goot and over at Satellus Iridium have been working to use Iridium signals to navigate. Actually, that was a spinoff of a project called iGPS, and I was one of the initial technical people on that. And they're the ones who took it to kind of a practice that works. They're using pseudo-range and Doppler shift, and the kind of performance they're getting isn't really quite as good as current GNSS. If you can get 20 meters, you're really happy. And that's when you're sitting still. If you're moving, now you need extra sensors, and it's tougher. Other people have looked at using LEO constellations. Zach Cassis and his group have done a lot of work, published a lot of papers in this area. I guess the most interesting thing about them is that they're actually out there doing it. They're out there using Starlink signals and some other kinds of signals like Orbcomm they've used. And but they have a different approach. They're using these as signals of opportunity and assuming pretty much you have a base station so that you can do single difference, both carrier phase and pseudo range, I think. So they are relying on pseudo range and they're relying on the space station. I'm going to talk a little bit later about what we rely on. We don't have base stations near the users, but we do rely on essentially some sort of ground control segment giving ephemeris and clock rate offsets for the constellation. Then Zurich, that's a European group that's also considering these. My own colleague, Matthew Jorger, and his group, who at Virginia Tech here, have been working with, they started working on the iGPS program, or he did, and they're still concerned about using LEO constellations. And Todd Humphreys and his postdoc, Peter Iannucci, are working the problem too. They're also receiving real Starlink signals, so that's interesting. We'd like to get there. We're not there yet. But none of these papers I've talked about so far are thinking of using only Doppler shift. And they're not thinking of using this without any other sensors and just a standalone system, point solutions. Other people have looked at that are Frank Van Diglen in his book on AGPS and an earlier patent or two. He pointed this out to me after the paper was published. So he's actually not cited in the paper, but he's gonna write a technical a comment about my paper to point out that he was already doing this a while ago. That was really just to kickstart AGPS with a rough initial fix. So if he could get within 100 meters per kilometer, he was happy. And we're gonna and he was using the Doppler off of MEO GNSS satellites, which is a problem. Okay, it limits how accurate you can get. It turns out, as we're going to see, you need these LEO satellites to be moving rapidly. And also his model is missing some terms, which are okay to be missing when you're only going for like a kilometer accuracy. But when you're going for like 5 meters accuracy, you need all the terms. There's another group, Morales Ferreira and et al. Did some work on this area, but they left out some terms in their model and assumed you were sitting still and had zero clock offset. Kind of a not necessarily reasonable assumptions. So they addressed it, but not so well. So now I want to spend some time talking about Doppler shift models. I'm actually going to present to you 3 different models with various uses for them. So first of all, you got to recognize that the measured Doppler shift, D sub j, j stands for the jth satellite, D is Doppler shift in hertz. You take the accumulated delta range, okay, which is a typical model. Basically, it's like a pseudorange model, except you subtract the ionosphere term rather than add it, and it has a bias. And you time differentiate it, but you got to be careful. You're time differentiating it in your receiver. So you're differentiating with respect to the erroneous receiver clock time. That gives you a range rate. You negate it and divide it by your nominal wavelength, and that gives you your Doppler shift model. And if we take that model and we put in a typical model for the accumulated delta range, and we do all the math, then we come up with this model for the carrier Doppler shift. We also multiply both sides of this equation by negative lambda. So we have negative lambda times d. And then this term on the right here of this equation is just this time derivative of the accumulated delta range with respect to the erroneous receiver clock time. Except I've neglected the time derivatives of the ionosphere and tropo terms that are in this accumulated delta range model. So you don't see any iono or tropo. And this capital TR, that's the true time. So capital TR equals little tr minus del r, which is the clock offset. So notice we have the unknown velocity, we have the known satellite velocities. These are all ECF coordinates. We have the unit vector that points from the satellite to the receiver. We have the rate of change of the receiver clock offset, the rate of change of the satellite clock offset. That rate of change of the satellite clock offset appears in more than one place. The rate of change of the receiver clock offset appears in more than one place. We have a fix-up term for the rotation of the Earth during the propagation interval. And that particular model, I think this paper is the first to publish that model in all its glory. And we developed that model, I don't know, maybe almost 18 years ago. Brent Ledvin, who graduated Cornell while I was there, I was on his committee, and now he's at Apple doing navigation there. I developed this model, and he and I went around with a Magellan receiver, riding around in the car, and collected a lot of data and came back and processed it all in MATLAB. And we were getting 1 centimeter RMS velocity errors with essentially zero bias. Because it was a really good PLL that was in that Magellan receiver, and you could integrate them for 5 minutes. There was so little bias. You integrate for 5 minutes, and you only get 1 or 2 meters errors. You can actually take these velocities, integrate them, and draw maps of where you were. And we were like, "Wow, this is really cool." We put it in the GPS course that Paul Kintner had established at Cornell, the late Paul Kintner, who was Brent's advisor at the time. And so we just said, okay, we're good at using, and so the idea is we navigated with pseudorange, so we knew the position and clock offset. And so many things in this equation were then known, and the only unknowns were velocity and receiver clock offset rate. So if you had 4 or more Doppler shifts, you solve for velocity and range equivalent receiver clock offset rate, and it really worked well. Now we want to do something different. We want to say, whoa, no, we don't know position. We don't know receiver clock offset. And we want to exploit the fact that that equation is also dependent on these 2 terms so that we can solve for all 8 of these unknowns: position, range equivalent receiver clock offset, velocity, range rate, receiver clock offset rate. Now that we're asking for more, though, of this equation than just velocity and clock offset rate, I felt it was unwise to neglect the ionosphere and tropo time derivatives. Now, maybe they can be neglected, I don't know. But first time around, I figured don't neglect them. But if you don't neglect them, when you go to take this time derivative, now you need those time derivatives of the ionosphere and tropo terms. I said, wait a minute, that's a bridge too far. So instead, what I did was I said, hey, I'm going to take an accumulated delta range model, which I'm really good at. Everyone once you got a model of pseudorange, you essentially got a model of accumulated delta range just by negating the ionosphere term, and adding a bias. And I'm going to form a 5-point finite difference of that with respect to erroneous receiver clock time to get essentially a numerical derivative that I can use in my model, because then I can have an analytic model for this and for its partial derivative with respect to unknowns. And then I can finite difference it. And this is, it looks like a 4-point finite difference. That's because these things are offsets to the true time. Delta TR is offset to erroneous receiver clock time, but we have to have an offset to true time because the input argument here is true time. And there's a offset that's 2 delta it's actually an increment to the erroneous clock time here. There's a -2, a -1, a +1, a +2. But the zero, the negative or plus 0 term has a 0 weight. That's why I call it a 5-point derivative, even though you only see 4 points. But in computing this, and this is the main thing that we use in the batch filter that's just defined later on in the paper. But you need this model then of accumulated delta range. So just to review what that is, this is in a lot of books. Accumulated delta range basically equals the true range, which is the user position minus the satellite position. But remember, we have to take the satellite position in ECF coordinates at the time of transmission and do this little rotation matrix. That's this rotation matrix to account for the amount that the Earth rotates. This is the Earth rotation rate during the propagation delay from the satellite to the receiver. So there's the true range. There's the effect of the clocks. There's the effect of the tropo, the negative iono, because this is carrier phase based. And there's the bias. But in this model that we're finite differencing in this previous chart, we actually have to iteratively solve for this propagation delay. So this is actually an implicit equation of the propagation delay. It appears here and it appears there and there. So you have to iteratively solve this equation where now the tropo term adds in order to get the propagation delay, in order to put it in here. But that's a pretty standard thing that you do when you're just doing pseudo-range-based navigation. So it's not so hard to add it to this. So that's our second model. But our third model is a simplified model that we're going to use only for GDOP analysis. And this third model, we go back 3 charts. We go to this first model, the one that we got good velocity and clock offset rate from. And if we say term like this transmitter clock offset rate, that's at seconds per second, it's around 10 to the minus 13th. So 1 plus that is pretty close to 1. And this thing is about 10 to the minus, this thing divided by C is about 10 to the minus 5th. So 1 plus that is pretty close to 1. And again, this is about 10 to the minus 6 or lower. So 1 plus that is pretty close to 1. So if we approximate this term, that term, and that term as being 1, which are not bad approximations, then we get our third model, which is this model. Now, I don't propose using this model for navigation because those things, you don't want to use that model and neglect something order 10 to the minus 5th. You take 10 to the minus 5th and maybe multiply it by the radius of the Earth. That's still too big a number. So you don't want to use that for actual navigation, but we can use this in a GDOP analysis because when we go to do a GDOP analysis, we're asking ourselves about the Jacobian of the measurement model with respect to unknowns. And things that are, off by 10 to the minus 5th, well, that's going to give you a GDOP answer that's off by 10 to the minus 5th from what you thought it was. Okay, we're not trying to get GDOP to 5 significant digits. We get it to 3 significant digits, we're very happy. So again, these are 3 models I'm going to use. So now I want to talk about the satellite. So because we have the constellations and how they might be used. So because we have 8 unknowns, we're looking to see 8 satellites simultaneously. And so we look at Iridium, which is already up there and operating. It's got 6 orbital planes, 11 satellites per plane, 66 satellites. They're nearly polar orbits, 780 kilometers altitude. Well, you can only guarantee to see one of those satellites at a time above a 7.5 degree elevation mass. Sometimes every 10 minutes you see 2, and if you're in between planes, maybe every 10 minutes you see 3 or 4, but you never see 8. So Iridium is not going to cut it. OneWeb, however, and this is just an initial version of OneWeb, where there's 18 planes, 40 satellites per plane, so a total of 720 satellites. all, again, nearly polar, 1,200 kilometers altitude. So each one sees a little bit more. Now, above a 7.5-degree elevation mask, you can simultaneously see 20, so that you're above 8. So bingo, maybe OneWeb is going to do it for us, all by its little self. Starlink, I'm talking now. By the way, how do you even know these constellations? Well, we got them from FCC filings. So they have to talk about their constellations in FCC filings, but they're kind of old, and then they don't necessarily update them. So it's kind of hard. Probably these numbers have changed somewhat, but I still think they're somewhat representative of what you could see. So an initial Starlink constellation was going to have 1,600 satellites, 32 planes, 50 per plane, not polar orbits, 53 degrees inclination. You can see 57 satellites above this elevation mask, but only if you're in a plus or minus 65 degrees latitude range. Because we only got 53 degrees of inclination, you get too high or too low a latitude, now satellites start dropping off. You go to the poles, you hardly see anything. Okay, because at 1,150 kilometers altitude, they only have a certain amount of footprint. Kuiper, 34 planes, 34 satellites, again, limited elevation, 51.9 degrees. So if you stay within plus or minus 60 degrees of the equator, you can see 17 or more of these satellites. They're lower down, that's why you don't see quite so many. Also, it's not quite so many satellites. But again, there are more than 8 if you're willing to stick to these ranges. Final Starlink's got a bunch of different inclinations up to 81 degrees, different numbers of satellites per plane, 51 planes, a truly massive number of satellites. And again, maybe Elon Musk wants to go even above that, but everywhere on the Earth, you're seeing 81 or more satellites above this mask. So certainly the final Starlink constellation is something to behold. It could really help enable this idea, because it's 10 times as many satellites as we need to see. So again, what I'm saying, I'm just basically all this stuff I've already said, except that you could use a combination of constellations. But just because there's enough satellites, just because something gives you 8 or more satellites, it might still have a bad GDOP. So we have to analyze the GDOP of the constellation too. So it's not just a question of counting satellites. Just like with GPS, it's not just a question of counting satellites. You might see 10 satellites, but if they're in a terrible GDOP, that's not doing you much good. Although I guess if you see 10, unless you're in an urban canyon, you probably have a pretty good GDOP nowadays. Just to further illustrate this is from my student Brian McLemore made this. And this is an illustration of that OneWeb constellation. So there's 18 orbital planes. So between ascending and descending nodes, there's a plane every 10 degrees. So these red lines here are the planes. The red circles are the satellites in the plane, 40 of them per plane. And then there's magenta footprints that show the footprints of what can be seen above a 7.5 degree elevation mask, what part of the Earth can see that. And just to illustrate, here's one particular plane in yellow, one particular satellite is a yellow asterisk, and its footprint. Everybody within that footprint can see that satellite at 7.5 degrees elevation or higher, as long as they got a clear view of the sky. Okay, so you can see these are massive, there's massive coverage from these things. So one of the first things I did was just consider a batch least square solver that said, if I do see 8 or more satellites, n is the number of satellites I see, let me develop a batch least square point solution cost function with unknown position, unknown range equivalent receiver clock offset, unknown velocity, unknown range rate equivalent receiver clock offset rate. That's a mouthful, isn't it? Okay, so there's 3 elements of that. That's a scalar. 3 elements of that. That's a scalar. There's 8 unknowns. You want to solve for them. Basically, you compute the error between what your range rate is and what your Doppler predicted it could be. Remember, the range rate, the negative lambda times dj is a prediction of this. You divide by the standard deviation of that. That's a negative log likelihood cost function. Square the error, sum over all of them, minimize it. And when you solve it with Gauss-Newton, you need a first guess. There's the Gauss-Newton has a convergence robustness enhancement where we do a line search along each step. And we developed a test case for this filter where we simulated the final Starlink constellation where you can see at least 81 satellites everywhere. We assumed that you had a Doppler shift measurement error precision that when you multiply it by wavelength gave you a 1 centimeter per second range rate equivalent measurement error standard deviation. Of course, the actual value depends on your received carrier to noise density ratio, and your accumulation period. And if you're using a frequency lock loop or phase lock loop, it's bandwidth. And above a 7.5 degrees elevation mass, we see between 181 and 197 satellites. We didn't model any errors of the ionosphere or the troposphere model. So we used models, but we assumed that they were perfect. And we did 100 random cases distributed equally over the globe and distributed in altitude from 0 to 30,000 feet or 9144 meters. And we simulated we had randomly chosen velocity components of the user equipment, chosen from a Gaussian with a mean of 0 and a standard deviation of 137 meters per second. So when you get out to 3 sigma, you're like going at the speed of sound. And we had 100 cases with perfect satellite ephemerides and transmitter clock frequencies between the filter and the simulation. But we did another 100 cases where we assumed that the filter had the wrong satellite positions with a 2 meter RMS per axis error, the wrong satellite velocities with a 0.002 meters per second RMS per axis satellite velocity error, and a 3.3 times 10 to the minus 11 second per second RMS satellite clock frequency error. That's frequency knowledge. And so here are results for those cases. Here, the first line is for the 100 cases without any ephemeris or clock frequency errors. The second line is for 100 cases with them. And then the columns tell different performance metrics. So first of all, everything converged, the batch filter converged. By the way, we started the batch filter off up to 143 to 151 kilometers away in latitude and longitude. Altitude, we always started at 0 altitude, even though the altitude could be anything from 0 to 9144 meters. It always converged. Mean number of iterations was 8.4 for the one case, 8.3 for the other. Maximum was 17 for the case with perfect ephemeris, 14 for the case with bad. The RMS of the position error, we took the difference between the true position from the simulation and estimated position and took its magnitude of that error and took the RMS over all 100 cases. It was 1.35 meters for the perfect ephemeris case, 2.27 meters for the bad ephemeris case. The maximum error is 4.16 over the 100 cases, 5.43 meters for the 100 cases perfect ephemeris, 100 cases imperfect ephemeris. And velocity error is down around centimeter per second level, but the maximum up around 2 to 4 centimeters per second. These are all GPS-like accuracies, standalone GPS accuracies. But when we get to clock offset, we're talking, 2/10, 3/10 of a millisecond, not microsecond. RMS error, 5/10, 9/10 of a millisecond maximum clock error. So this is quite a few orders of magnitude worse than GPS. And we'll see why that is momentarily. So now I want to analyze this and do a generalized GDOP analysis. And this analysis puzzled me for a while, but once I got it to work, I was really happy about it. It's I'm most proud of perhaps this piece of work in my whole profession, or it's one of my most proudest pieces of work. Let's put it that way. And the way you do a GDOP analysis in traditional GNSS is you have a linearized model that relates your perturbations, your errors, these delta D1, delta D2, up to delta Dn. Those are our errors in the carrier Doppler shift measurements. And we're assuming that they're all zero mean with a standard deviation, and they're uncorrelated, and they have a standard deviation of lambda times sigma dop. And then there's a relationship between those and our estimation errors. This is our estimation error position, estimation error receiver clock offset, estimation error of clock off of velocity, estimation error of range, rate equivalent clock offset rate. And this matrix here, this is a big challenge. This matrix has n rows, 8 columns. This is typically the matrix that you would then multiply it by its transpose, invert it, take the trace and take the square root of the trace, and that would be GDOP. And in fact, these last 4 columns are exactly that matrix that you would do that with to get GDOP for traditional pseudo-range GNSS. But these first 4 columns are different. Remember, this is 3 columns, 1 column, 3 columns, 1 column. And the difference is these are all non-dimensional. That's a unit vector. But these things have units. That has units of per second or radians per second. And this has units of meters per second squared. So this matrix is not non-dimensional. The other problem is these things have units of meters per second. Those guys have units of meters per second. But these guys have units of meters, that's units of seconds. And ideally in a GDOP analysis, you want this matrix to be non-dimensional, and you want the dimensions of this vector and of course the dimensions of that vector all to be the same, and all the elements of this vector to have the same dimensions. So the deal is we need to find a characteristic rotation rate in radians per second to multiply by delta R and then divide this column by that to get this thing in a meters per second unit, this thing non-dimensional. And we need a characteristic acceleration to multiply by this clock offset to get this in meters per second, divide this column by that to get that non-dimensional in order to do a real GDOP analysis. So it turns out we can get those. And this was the really exciting thing to me, that you can get these things. Uh-oh, I'm having a problem here. You can get them, and the way you get them is assuming a circular orbit for your satellites with a certain semi-major axis, A orb, above a receiver on an Earth that's basically radius of the Earth away from the center of the Earth, and you assume the Earth is not rotating, and then that characteristic rotation rate is the maximum rotation rate of this line of sight vector from the satellite to the receiver. It's the maximum rotation rate that will occur in the circular orbit with this differential radius. Here's where the receiver, here's the satellite is. And that occurs, of course, when the satellite's directly over the receiver. And the maximum occurs only, of course, the maximum doesn't occur if the receiver isn't under the satellite plane. But here's that maximum. It's gamma, it's in radians per second. So you take the mean motion, radians per second, and divide it by this non-dimensional factor, 1 minus the radius of the receiver divided by the radius of the satellite. And that's in radians per second. And then this maximum acceleration, this is the maximum acceleration of this range for any satellite in the circular orbit. And of course, it occurs when the satellite's directly over the receiver, and it occurs because if the orbit passes directly over the receiver. And that is basically the acceleration of gravity at the satellite altitude multiplied by this geometric fix-up factor. All of these things, it turns out we want both of these to be as large as possible to get good accuracy. And you can see that the smaller A gets, this thing will get larger and that thing will get larger. This is what's dictating, the fact that we want both of these to be large is what's dictating the use of LEO satellites here. So now, if we multiply delta R, the position error, by this radians per second gamma quantity, now this is in meters per second, we multiply delta del R by this meters per second squared maximum acceleration. This is again in meters per second now. All these things are in meters per second. All those things are in meters per second. But in order for this equation to be true, we have to take that original matrix and divide the first three columns by gamma. So that's what we do here. And take the original matrix, divide the fourth column by eta. That's what we do there. And we call this the GDOP matrix. And now all of its elements are non-dimensional. We can transpose it, multiply it by itself, invert it, take the trace, and call that a generalized GDOP. Now, there's something though, there's something more that we have to do that we don't have to do with traditional MEO. We have to take that GDOP and decide what it means about precision for position, clock offset, velocity, clock offset rate. So in traditional GDOP, all you do is multiply it by the pseudorange measurement error standard deviation in meters, and you get the position, roughly the position precision in meters, and C times del R precision in meters. But now, if we multiply by the range rate equivalent error standard deviation, so error of Doppler shift in hertz times the wavelength in meters per cycle, that's an error in meters, that's a range rate error in meters per second. We have to divide it by this gamma to get a range error. So we take this nominal range rate error in meters per second divided by gamma multiplied by GDOP. That gives us the precision of R. Take the thing, this same range rate equivalent error standard deviation divided by eta. That gives us a precision of the clock offset. We don't have to divide it by anything to get the precision of velocity. We get divided by C to get the precision of del R dot. It turns out when you do this, these precisions here are consistent with all the results in this table. So this really does work. And by the way, when you do this, if you redimensionalize this matrix here, if you redimensionalize this A transpose A, G dot, A transpose G dot, A G dot inverse, or redimensionalize it, you should get a very good approximation of the standard covariance matrix that you would get in association with this batch filter. And in fact, you do. And in fact, that same equivalence holds when you do G dot for a traditional set of pseudorange equations. So now, here's a G dot map of that final Starlink constellation. Here's longitude, latitude, and there are, G dot is basically below 2 everywhere. And by the way, you also have to give the gamma average. By the way, because Starlink has several different altitudes, we had to use an average gamma in this analysis and an average eta. Average gamma is 0.006 radians per second. Average eta is 37 meters per second. That was used for all the GDOPs. If we have GDOP of 2, and we multiply it by a range rate error of 0.01 meters per second, now we got 0.02 meters per second, then we divide it by this, so 0.02 divided by 0.006 is about 3.3 meters RMS range position we'd expect. And that's what we saw. Now this thing is a little hard to view, so if you view it sideways, and I did actually a bunch of different 4 different Monte Carlo cases, which were just where I was twisting the Earth relative to the constellation. And now we're just worried about latitude here from -90 to +90, and we're taking the minimum GDOP and maximum GDOP over all longitudes and over all the 4 different cases of where the Earth was relative to the constellation. And we see we got GDOP, best case is about 1.15, worst case is about 1.9. So that's for Starlink. For the initial Starlink, we only have the 1600 satellites, and we only go up to plus or minus 57 degrees. We got a good, and again, this is the same kind of a summary plot where I did a lot of different points on the surface of the Earth, and I took this is versus latitude. I've taken the minimum, maximum over longitude and over 4 different Monte Carlo simulations of where the Earth was twisted in longitude relative to the constellation. And we see, between plus or minus 50 degrees, we get pretty decent navigation, GDOP plus or minus, about not much more than 2. But as soon as you go much above 50 degrees, now GDOP gets bad. Same thing is true for Kuiper, a slightly different region. Now, here's for OneWeb. This is very interesting. This was, when I first saw this plot, I didn't understand it. I thought I made an error. What's wrong with me? This is GDOP versus latitude and longitude for a OneWeb constellation. This is a OneWeb, remember there's 18 planes. This is a OneWeb constellation where all of the 18 planes have their ascending nodes grouped on one side of the Earth and their descending nodes grouped on the other side of the Earth. And when you do that, it turns out at high latitudes, you're fine. You have low GDOP. But at mid latitudes, if you're in a place where you're seeing all ascending nodes or all descending node orbits, you got lousy GDOP. The only place are these corridors where you're in a place where you're seeing both ascending nodes and descending nodes. And that has to do with the fact that the geometric diversity of your line of sight vectors is fine, but the geometric diversity of the line of sight rate vectors is bad. They're all going the same way. And when you're here or here, but here you see some going north, some going south, and now you get a decent GDOP. But if we fix that, if we say, no, let's interleave the ascending and descending nodes of the constellation, now we get back to this. This is worst case, maximum GDOP, minimum GDOP over all longitudes over 4 Monte Carlo simulations. But now we have alternating ascending and descending nodes. And all of a sudden we have not such a bad maximum GDOP, 4.3, rather than almost 100. So constellation design matters in this system. And just to sort of further illustrate that, here's an idea. So we were worried about the traditional unit vectors, rho hat 1, rho hat 2, rho hat 3, all pointing from the satellites to the user receiver. But we're also worried about the geometric diversity of their time rates of change. By the way, these time rates of change aren't unit normalized. All we know about them is that they're perpendicular to the corresponding vector. But their magnitudes can be anything, really. But as the satellite's going this way, the unit vector is rotating, sort of this tail is going faster than its head, and therefore its rate of change is pointed that way. Same with all these. this is actually a bad situation because both constellations are heading pretty much the same way. And so all these rates of change vectors, which are the things that are in the first three columns of our GDOP matrix, we're all pointing sort of the same way. That's not a good thing. Just getting ready to wrap up. Additional considerations. There's an elephant in the room that I didn't mention, and that's that these are communication constellations. And because of that, they have narrow downlink signal beams. So I've been working under the assumption that if a satellite was above 7.5 degrees elevation mass, then I could see them. Well, I can see them, but it doesn't mean I'm going to see a usable signal. Because if 81 of Elon Musk's satellites are all sending me signals, then that's a terrible waste of power. Only one of them needs to send me signal to communicate with me. And also you're wasting bandwidth. Now we might have overlapping bandwidths and we can't use all the bandwidth. And the same thing is true of OneWeb and all the constellations. So in order to conserve both power and bandwidth, they tend to be stingy about the footprints that each satellite can see. And so if we're just relying on the main communication signals, we're not going to see even 8 satellites at a time, even though maybe 20 are physically, we have line of sight vectors to them. Now, it could be we could use side lobes so that we don't have to see the main lobes, in which case the constellations can just do what they're doing and we're fine. I would really prefer the constellation owners. Some of them have FCC approval for these command and control beacons that are wide angle. Please turn them on every so often, and then you can supply navigation. There's also the possibility of using an INS to compensate for this limited simultaneous signal availability. And my student Brian McLemore wrote a paper. It's actually in review now at the IEEE Transactions in Aerospace Electronic Systems. We didn't consider the ionosphere and troposphere mismodeling. The downlink signals from these constellations, 11 to 40 gigahertz, they're not going to get through rain. They're going to be attenuated, scattered by rain, and attenuated by foliage. So again, if they could give us a beacon, the constellation owners, that was lower frequency, that would be great. Although maybe, who knows, maybe Iridium's going to put up a few more satellites at L-band, it will be good. Also, we don't know about multiple access properties, signal processing. So in summary, I'd just like to say I proposed and analyzed and simulated this carrier Doppler shift only global navigation satellite system. You got to see 8 or more satellites. You got to solve simultaneously in a point solution for 3 position components, receiver clock offset, 3 velocity components, receiver clock offset rate. Developed a generalized GDOP analysis for that. It looks like the system in theory could deliver, GNSS type accuracy, 1 to 3 meters RMS position error, centimeter per second velocity error. But clock sucks. It's going to be order of a millisecond or a little bit better. Now, if we should put up a pseudo range every now and then on a few satellites, we could fix this. You don't have to have it at all, and we're working that problem. So thanks for your time.
Okay, thank you so much for this great presentation. We already have a few questions. If you'd like to add a question here for Professor Psyche, please go ahead and click on the Q&A button in your viewer, and you can type your question there. We will get to those. So one of the first questions we have says, can the carrier Doppler shift be detected at these low elevations you're assuming? Where did the 7.5 degree elevation mask come from?
So if a signal, so the 7 point, I was just sort of, seat of the pants, hey, I know with GPS, we can use carrier Doppler shift down to 7.5 degrees. So, but I think just what I said in this chart here, this is basically saying you're not going to get nearly down to 7.5 degrees because, so for instance, the OneWeb constellations, they have this very narrow footprint of their main beams that maybe you're going to have to, the satellite's going to have to be maybe, I don't know, above 50 or 60 degrees to be in the footprint of that constellation. And it has to do with the antenna gain patterns of the signal. Starlink is a little better because Starlink has these steerable beams, but they might not steer beams from many satellites at you. I think Todd and Peter Iannucci and Todd Humphreys say, I don't know, maybe it's out to maybe 2 satellites are going to steer their beams at you at the same time. So this is the real bottleneck. If they put beacons on, if they were to, actually they might have the beacons, if they were to turn their beacons on though, almost certainly we can get things down to 7.5 degrees. It really depends. Or it may be because remember, these are not weak GPS signals. They're trying to cram an awful lot of bits down in their communication signal. It takes a lot of power to do that. So their main lobes are very, very hot. So their side lobes might be strong enough that we could get Doppler down to 7.5 degrees, but that's a conjecture. I have absolutely no data to prove that. And it may be ridiculous. I don't know.
Okay, great. Thanks for that answer. And you were just talking about Starlink, so we'll go ahead and jump to this question, which says, for Starlink, how do you take the narrow pencil beam spot sizes into consideration for detecting their Doppler signal of opportunity? And how does this affect the number of satellites you can see at a given time?
Okay, so almost certainly. So we've been told by Todd that that Starlink is probably going to steer 2 spot beams at any given location at any given time, because they're afraid one might be attenuated by foliage, and so maybe the other will get through. So if all you can do is hear a Starlink, and Zach Cassis has data, or one of his students has data that basically backs that up. So if you're using their main lobe signal, you're not going to get 8, you're going to get 2. You're certainly not going to get 81. But the question is, could each of those main beams, beams are not perfect. They have side lobes. Again, there's a lot of power coming down in those beams. So if we can see their side lobes and do some special processing with the side lobes, maybe we can get down to, we can get more than 2 beams. Whether we can get 8 or more, or whether we get down to 7.5 degrees, I don't know. Let me say I'm leaning skeptical on that. If you put, these things are advertised, when I'm saying this, please put omnidirectional beams on them. Please put lower frequency beacons on them. I'm hoping Elon Musk or somebody at OneWeb is listening and will say, oh, gee, we can be a navigation system too. And the FCC did let us put on these omnidirectional beacons, and you have to turn them on all the time. You could turn it on maybe once a second for 10 milliseconds. And so you'd have a 1% duty cycle, and you'd have a global navigation system. So again, but if it's untrue that we can get the side lobes, and if they don't put these things on, we're sunk. This isn't going to work.
Okay, great. Thank you. So we have a few more questions to get to here. First, a comment by Ranwa Haddad, who said that GPS constellation designers are very careful about GDOP. And a question from Andrew Dempster, which says, when you normalize the elements of the GDOP to make them unitless, is there an assumption that each measurement type makes an equal contribution to error? For this to occur, you need to define a unique normalizing factor.
Yes, that's a great question. Let me go back to that equation. So perhaps you don't recall, but I assumed, so there's only one measurement type here, Doppler, right? And I've assumed that each of these Doppler shifts from each of the n satellites has exactly the same measurement error standard deviation. And of course, you multiply it by lambda, it becomes a deviation in meters per second, and standard deviation in meters per second. And I've assumed that they're uncorrelated, which is also the standard basic plain vanilla assumption that you make for GDOP for pseudorange equations. You start out assuming all the pseudoranges have the same measurement error standard deviation, and their errors are uncorrelated. Now you could do a fancier one that say, wait a minute, some of them have lower carrier to noise density ratios, or they're lower elevation, therefore more multipath, and you could change that assumption. But the most basic GDOP assumption just makes that assumption. All the measurement errors have the same standard deviations for all the measurements, and they're uncorrelated. So I'm really just carrying through that assumption. And admittedly, you can improve on that, but it does give you a rough idea of how things will work out.
Great, thank you. Let's see, let me go to one of the questions I just scrolled past. Give me one moment here. Here it is. How would you physically capture the observable in hardware? Is a known pseudo-random code required like GPS?
So that's a great question. So if so first of all, we don't know if there are preamble. So if you're in a main beam and the beam has some sort of preamble in each of its bursts, you could work off of that preamble and use that as, quote, the known pseudo-random code of a message. Or if it's, I think a lot of these things are OFDM. And so these OFDM signals tend to have reference signals with known bit encodings on those reference signals. So you can use those as though they were a known PRN code. If, however, we in a system where we're going to try to use side lobes, first of all, those reference bits might be the same reference bits that are in the main, the signals whose main beams you're getting. So they'd be interfering with each other. You would, and you wouldn't be able to separate out, get essentially multiple access. So in that case, the assumption is that either that you would somehow basically buy some time and broadcast essentially prank phone calls on these things that, you know, you told Elon Musk you wanted to send some signal to somebody, but the truth is you weren't. It was essentially a PRN code that you had created and known ahead of time, so that your receiver would have something like a known PRN code with which to get processing gain if you're trying to process a side lobe signal. So main lobes, I think it's pretty easy. I think they're OFDM signals. You use the known reference signals. Side lobes, you've got to do something extra. Now, the Constellation operator wanted to help us and said, no, we can't put on these beacons. We even though we got the FCC approval, we did not actually put them on, but we do want to support navigation. The Constellation operator themselves could use a little bit of their bandwidth to send out these, quote, pseudo-random codes, so that in hopes that the side lobes could then be processed. If it's possible, it may be there's other issues that cause that, like for instance, the near-far problem. You know, so you've got a PRN code on a side lobe, but you still got a main lobe that's making an awful lot of power in the same frequency band. Maybe there just isn't enough processing gain to overcome that power differential. I don't know. Okay, it's a question I think that deserves consideration, because but what the answer is going to be, I have my hopes, but I don't want to be too optimistic.
Okay, great. Thank you for that. Let's see. Do these constellations estimate and broadcast their ephemerides, at least so you can compute satellite velocities with needed or assumed accuracy? Are there any concerns about the accuracy of the nominal satellite center transmit frequency?
Oh, absolutely. So it turns out that these position error and velocity errors, they're not so much important in this assumed ephemeris errors. This is the thing that's more important, the satellite clock frequency error. And it may be a stretch to do that. So the assumption of all of this is that there's something like a ground control segment operating for this constellation or set of constellations. And it could be operated by the constellation owner, or if the constellation owner is not cooperative, it could be operated by somebody else. And then you have to figure out the orbits to get something like this level of position accuracy, velocity accuracy, and clock offset accuracy. Although there are reasons to believe we could maybe relax this by half an order of magnitude, get up to like 10 to the minus 10th seconds per second. And it's a prediction. It doesn't have to be, you have to predict it. So you've had a ground control segment, it's estimating and predicting, and now you need some sort of link to get that information to the users. And this is where I diverge from Zach Cassis's group, because they're assuming you have a reference station right there in the same locale as a user. And I would rather have this be a global system, but somebody has to stand up the ground control segment that figures out these things and some sort of communication link. But it could be that Elon Musk was not cooperating. We could buy time on his satellites, or maybe buy time on Iridium to send this information over. So there are ways it can be done. How convenient that would be, how much Iridium bandwidth you would need, how often, whether you could predict for 2 hours and not send so many bits, or you can only predict for 10 minutes. Those are open questions. And the answers to those will determine the practicality of this.
Okay, our next question says, what were the lengths of your simulations? And a follow-on question, would the high frequencies be susceptible to environmental interruptions?
So let's answer the first one, the second one first. So if we go back to this, in fact, the high frequencies are going to be much more attenuated by foliage, scattered by rain. Oh yeah. So even if we got this whole thing to work, Elon Musk agreed, he helped us, he did either steer a lot more spot beams to us, or he gave us PRN codes and we could deal with the side lobes. You still got a foliage problem here. You still got a precipitation problem at these frequencies. That's why I'd really like them to turn on a lower frequency beacon, because then we can have some kind of availability without worrying so much about foliage and rain like we have currently with GNSS. But if we have to stick with the communication signals, these are going to be a problem. So that's the first question. Second question first. Remind me of the first question again. I had an answer to it, but Rick, can you reread the first question?
Oh, yeah. Sorry about that. Let's just come back up here again. Sorry, I lost my place. Oh, sorry. Yeah. What were the lengths of the simulations?
So remember, this is a point solution, okay? So the length of the simulation were essentially 0, or you could say they're the length. By the way, I'm assuming for this thing that you're basically, rather than running a PLL, you just basically get a burst of data, and you do. There's a way to do an frequency discriminator on a burst of data. You sort of have, just like you have early prompt and late for pseudo range, you have guessed frequency a little bit lower than the guessed frequency, a little bit above the guessed frequency, and then depending on carrier to noise ratio and burst length, you get a certain, for an optimal estimator, you get a certain frequency standard deviation from that calculation. And because remember, these are just point solutions. I just need to know. I want to know position, clock offset rate, velocity, position, range equivalent clock offset, velocity, range rate equivalent clock offset rate at an instant, and I just need to know the satellite position that goes into here, and velocity and satellite clock offset rate at an instant. So each of these 100 simulation cases is just a snapshot. Because remember, this is a point solution. There's no recursive filtering whatsoever. Now it may be that it would be wise if we can't get the clocks, if the clock errors are going to be worse than this, it may be wise to develop a recursive filter where the only thing recursive, you say, well, maybe this thing is kind of an error, but I'm going to estimate the clock offset rate for these satellites that are passing over me right now, and I figure it didn't change. Whatever it was, I didn't know very well, but it didn't change very much over over say 20 seconds. And then we might be able to deal with much larger errors here, but then it wouldn't be a point solution filter. It would be some kind of recursive filter.
Okay, thank you. We have a few questions asking about potential for spoofing. Could this concept be free of spoofing? Is there any considerations regarding security or authentication? What type of level of effort would be required to spoof one of these signals?
Spoofing. Oh, who would ever do a thing like that? So spoofing essentially is an orthogonal issue. It depends. So if a constellation operator stood up their beacon signal and decided to broadcast a secure PRN code on it, it couldn't be, it could be meakened, but it couldn't be spoofed. If they sent essentially PRN code-like things that you were supposed to lock onto through their main communication systems and had some sort of securities so that only authorized user could do it, or some navigation message authentication system, again, it would have the levels of protection provided by those things. That's sort of open to discussion. If, however, we don't get any cooperation from the constellation and we don't send any of our own PRN codes over it by buying communication time on it, and we're just using the reference, the bits from these things, oh yeah, spoofing is definitely possible, especially for side lobes, which weren't going to be very strong. The main lobes might be a little harder because they're so strong. But if we're just working off the reference frequencies of the OFDM signals, yeah, very vulnerable to spoofing.
Okay, great. Thank you. Well, and I think that also ties to this next question, which is what are the advantages of this over standard GNSS systems like GPS? Given the disadvantages of this approach, what are some useful ways to think about approaching this? We have some comments also from, let's see, tied into that. Is there a business case for a provider like Starlink to offer a PNT service, turning on the low frequency beacons? So we'll let you address those.
Well, if I were Elon Musk, I'd turn this on and I'd make all of my Tesla cars use it, and I'd have a secure signal going down to those Tesla cars. And then I could say, hey, my navigation on my driverless cars is more secure than anybody else's, except maybe the US military. So that it's not so much, it's a way to make Tesla automated driving more secure, because of course, he could have a, secure key between his cars and his satellites. And repeat the rest of the question.
Oh, sorry, just the question about what would be the advantages of this or disadvantages when compared to a GNSS?
So if you had the main lobe signals are so much more powerful that they're harder to jam. But if we're talking about side lobe signals, it's less clear. But the main lobe signals are much harder to jam because they're just so much more powerful coming down. Of course, they can be attenuated by foliage. Just the fact that because it is this, so supposing you were Elon Musk and you were providing a secure service and somebody hacked your service and now they could spoof your Tesla cars. Hey man, it's a communication system. Tomorrow you've got a completely different set of encryptions up there because it's a communication system and the hack is solved, Whereas GPS now, if someone hacks M code or PY code, we're in deep doo-doo.
Well put. Yeah. Okay. Well, thank you very much. We still have a few more questions, but we've reached the top of the hour again. So thank you so much, Professor Psyche, for your time today. We appreciate all you've done.
Okay. Thank you. It's been a pleasure.
And for those of you who are watching, we have recorded this webinar and it will be available on our website today or tomorrow, along with Professor Psyche's slides. And Mark, I don't know if you have an email address if you want to put up for anyone to contact you. So mlpsyche@vt.edu. Is that right?
Yep.
Okay, great.
And you're glad you're not in my class, right? That's an excellent. Okay.
Well, thanks again for your time, and we appreciate all those of you who've tuned in to view. And thank you. Enjoy your afternoon and evening.
Okay. Thanks a lot.